Hello, welcome to another example problem solving day. Example problem solving day. That works. I can speak. Welcome to another day of problems. Today we're going to do problems from chapter 11. Um, all the problems I'm going to do today are all old exam problems. Traditionally on the exam, I'm going to basically go one of two routes. I'm either going to go the solid liquid route with these equations in the upper left, or I'm going to go the gas route with the equations to the right of that. And as I said, all of these problems have been on an exam before, which means they won't be on an exam again. I never reuse problems, but something similar might be. And I'm going to kind of break them down into halves. I'm going to start with the solids. So that'll be, these equations. And then I'm going to go to the gases with these. It's of note with the solids that there isn't much going on with that equation. So I normally have to add some extra stuff to make it, worth 25 points. Though I'll show you what I mean by that as I get into it. So the short-lived TV show Firefly had a ship called Serenity. And Serenity was called a Firefly type spaceship because its back glowed hot. Working out what color it glowed, we can see that the engine, and I guess I did the math here just for this problem, that the engine was probably at about 1,310 degrees. Let's say the ship is made out of steel, and that the length of the ship was 81.9 meters when it was at room temperature. When this thing heats up to 1310 degrees, how much longer is it? Given that the coefficient of thermal expansion for steel is 11 times 10 to the negative 6. Okay? So that's the general question. If I want to solve for this, this is length elongation. The idea for length elongation is just right here, that the change in length is L naught alpha delta T. Did I write that in a different order? I wrote it in a different order. I could also write alpha L naught delta T. I usually write it this way. Why is my... Sorry. And I'll just plug in. L naught was 81.9 meters. Alpha was 11 times 10 to negative 6 inverse centigrade, inverse Celsius. Final temperature minus initial temperature. And I can do that math. And then you get that it'll be 1.16 meters longer. Now, part B. If the ship was made in such a way the steel could not stretch, what impossibly large stress would result from this temperature change? Okay. When I do problems with solids, I sometimes also work things in with pressure, where pressure is force over area. But a lot of the times I work in something like this. And this goes back to what we learned in chapter 9. In chapter 9, I introduced the equation that said F over A equals Y delta L over L naught. What this said is for the stress you put on something is Young's modulus. The stress you put on is Young's modulus times strain. In this equation, this F over A, that is stress. Now, I don't have this equation up on the top right now because, once again, it's from an earlier chapter. I just didn't grab it. But I often work this in with the chapter 11 problems, even though it's from chapter 9, because it uses the same idea. Now, one easy way to tell if you have to use this equation, if you ever see Young's modulus show up, you're going to use that equation. It's the only equation with Young's modulus in it. And so if I want to find the stress is F over A. And so F over A equals Y delta L over L naught. So it'll be Y 20 times 10, 20.4 times 10 to the 10 pascals times the change in length, 1.16 meters, over the initial length, 81.9 meters. And that gives me 2.89 times 10 to the 9th pascals. There's the answer. I'm not solving for F. I'm not solving for A. Stress is F over A. So that's my value. Just so you know, fun fact, not really fun, but whatever, it's a fact. If you convert that to ATMs, where one ATM is air pressure, you get 28,500 ATMs. That is 28,500 times the air pressure of, pressure of air. That's like deeper than the deepest parts of the ocean type pressures. Any questions? Okay, let's go to the next one. This next one is also an old exam problem, but it's a much older one. And to be honest, it's a little more difficult than I've done in a while. It's still a doable problem, but yeah, it's just a little harder than what I normally put on the exam. And it says, according to the comic books, Johnny Storm of the Fantastic Four can hit 1 million degrees Fahrenheit, which is stupid. But 1 million degrees Fahrenheit, that is a temperature of 555,538 degrees centigrade. If he started at room temperature and goes to this temperature, what is the change in length of his femur? Well, femur is the longest bone in your body. Now, I said what the Young's modulus for bone is. Not Young's modulus, sorry. The coefficient of thermal expansion, wrong value. The coefficient of linear thermal expansion for bone is 8.5 times 10 to negative fifth, because that is a known value. And a femur, this is actually a pretty average length. I worked it out from his height according to the comics. Seriously, I have way too much of a problem researching things for these problems. The amount of time I spend researching fictional characters is ridiculous. What would be the change in length? Now, if you look at this, I say, note this number is not realistic. So we know we're going to get something stupid here. Let's solve for it. And you get 20 meters, which is dumb and not realistic. Also, keep in mind, long before this temperature, you would burn to an ash. Actually, you'd destroy the planet if you had something on the planet being that temperature. But you know, minimal details. Part B is a lot more interesting. Part B says, well, okay, let me go back a step. Your bones won't really expand that much, even if you go up in temperature. First off, your body temperature won't change that much. You know, worst case, you have the flu. So I shouldn't really make light of these days. But if you have the flu and your temperature goes up, you know, your bones will not be changing much. But even if we go something like this, well, things would burn before anything else. But we're ignoring that because superpowers. Bones in general break anytime their stress exceeds 130 times 10 to the 6 pascals. That would be a stress, where stress is force over area, of 130 times 10 to the 6 pascals. What happens is your bones can't really expand because your muscles will hold them in place. That's what I was trying to say. That your muscles, ligaments, all stuff kind of keep things from really expanding. Because they'll expand too, but not nearly to the same rate as bones will. And I'm going to say this is the max stress he can get. What's the actual hottest Johnny Storm would be able to reach? Now, if I want to solve that, if I want to find the max temperature he can reach, I'm going to first figure out the max change in length he can get. You see, I know that stress is Young's modulus change in length over L naught. Once again, I know how to use this equation because I gave Y. And what I'll do is I'll use this to find delta L. I'll take my F over A and multiply both sides by L naught, divide both sides by Y. And that'll give me a change in length. That is 130 times 10 to the 6 pascals. I'll multiply by the initial length. .442 meters. And divide it by Y of bone, which is 1.8 times 10 to the 10th pascals. Note that I'm not doing F divided by A. F divided by A is that number. Stress is that. I could have also plugged in a P there if you really want it. And I'll get the maximum length that this could try to change by 0.003192, which is, slightly less than 20. Now that I have that length, I can go back to my delta L equals L naught alpha T minus T naught. And its question is, what temperature can he reach? I'll just solve this for T. See, what I can do is I can divide both sides by L naught alpha. And then add T naught to both sides and say the temperature he reaches will be delta L over L naught alpha plus T naught. Which means the temperature will be, am I off the bottom? No. Will be delta L 0.003192 over L naught, which was 0.442, times alpha, which was 8.5 times 10 to negative fifth 1 over degrees Celsius, plus 20. And you'll get 104.96 degrees Celsius, or 105 degrees Celsius, which still is pretty hot. That's the water boils. If you get 105 degrees Celsius, that it's real bad. It's real bad. But I mean, it's not put things on fire temperatures. It's not realistic. Well, it is more. It's not realistic for a human to get that hot, but it's not like superhero heat either. Questions? Okay, that's really the solid bit. If I do the solids, expect Young's modulus to show up. The problems are too easy without it. Gases, on the other hand, are a horse of a different color. This first problem. Okay, I want to be honest. This first problem is too wordy. There's just too much words on the page. I used to have a problem with making my problems too wordy. I now make sure I don't do that. But this problem was really written as kind of a fuck you to some students one semester, and I will fully acknowledge that. Because just when I wrote this problem. But let's start with part A, and then I'll get into the fuck you part. And it says, a regulation football in the NFL should be inflated to an absolute pressure between 27 and 28 psi and a volume of that number. If a football is filled to the minimum 27 psi, okay, pressure is 27 psi. That's not an SI unit. I need to convert that. But I say at the very bottom that 1 psi is 6,895 pascals. That's all the way downhill. At room temperature, how many air molecules? How many air molecules? Okay, this is talking about air in a football. This is a gas. Gases will be the ideal gas law and its friends, these equations. If I know the volume, pressure, and
your audio isn't coming through.
My audio is not coming through.
There it is.
Okay,
there it is.
Cool. So when did you guys lose me?
You started the problem, but you didn't write anything down. You were talking about starting it.
Okay. So I will move back a bit. I apologize for that. I'm still recording. I have no idea what just happened. I blame the internet. So this problem, I don't know what I said, so I'm just going to go over. Basically, this was about a gas. We're talking about air inside a football. And if I'm talking about air inside a football, that's going to enter into the ideal gas law equations. These equations. Well, only the top one's the ideal gas law. They don't just about gases in general. This is going to get into air as opposed to length of elongation. And what I said here, and I actually didn't mess up something here, is that I say this is the volume of a football, which I wrote down. If it's filled to a 27 psi, now psi is not SI units. I need to convert that, which I started converting it and didn't finish it. 186,165. Sorry, I kind of didn't give myself space. I wasn't thinking. If it's filled with 27 psi at room temperature is 20 degrees Celsius. I always give that value, though I should have added a sig fig though. Except when you're doing gases do not work in Celsius. The SI unit for gas is not Celsius, it's Kelvin. If I do anything with gases, you must convert your Celsius to Kelvin. I'll add 273 to get 293 Kelvin.
Oh, I have a question.
Yeah.
When you're doing solids, it's okay for it to be in Celsius, or that's Kelvin too?
The reason why it's okay for solids is that all the solids equations have a delta T in equation. Why are you not? Am I not sharing my screen? I am.
I can see just the football and I think like text messages in the background.
I'm sharing the wrong screen. Ba-ba!
Got it.
There we go. Sorry, I have dual monitor and I was just sharing the other monitor. Okay, so the reason it's okay is that the solid ones have these delta T in them, a change in temperature. And because we're doing a change in temperature, it's the same for Celsius and Kelvin. So solids are okay in Celsius, but gases don't have a delta T. They just have T, so you got to change them. Wow, I'm just really messing up today. So that's what we know. I want to solve for the number of molecules. If you want to solve for the number of molecules, that's the ideal gas law. PV equals NKT. What I would do is I would divide both sides by KT and say that N is PV over KT. And N, that would just be its pressure, which was 186165 pascals, times my volume, 0.004237 PV over K. Now K is Boltzmann's constant. I wrote it right down on this page. That Boltzmann's constant is right there. Times my temperature, which, as we were just saying, has to be in Kelvin. I don't think I had the screen up correctly when I was doing it, but I converted to Kelvin by adding 293 or 273. And I can do this math. Right, okay, 1.951 times 10 to the 23rd atoms. Okay. Now, before my internet cut out, I don't know how far I got into me talking about how this problem was kind of a fuck you to some students. It's kind of a dated reference now. I should probably update it to a new one. But in 2015, which is when I put this on the exam, there was a thing where the Patriots won the NFL AFC championship. And it was, the quarterback was accused of deflating footballs and having them have less than the minimum PSI. That the minimum PSI in a football is 27 PSI. He was accused of having less than that. And because he had less than that, it makes them easier to catch. And what they said is that his footballs weren't 27 psi, they were 25 psi. Now right there, 25 psi, I can convert that. 1 psi is 6895 pascals. And doing that conversion, that's 1,72375 pascals. Now, it was pretty cold that day. And so what the Patriots claimed as a team is they didn't underinflate the balls. They filled them to exactly the minimum, 27 psi, in a warm room. They said they were filled at room temperature inside. So they were filled when the temperature was 20 degrees Celsius to 27 psi. What happened is they brought these footballs outside, and because it was cold, the pressure went down using the ideal gas law. And that he said that the reason they had this psi was just because how cold it was outside. So let's use these numbers. If the balls were filled at 20 degrees Celsius to the 27 psi, they have that many molecules available. Let's say we bring them outside. What temperature would it need to be outside for this to be true? See, what I'm going to do is I'm going to say N doesn't change. This is still N. And the volume of the football doesn't change. This is still V. I'll solve for my new T. I'll say PV equals NKT. Divide both sides by NK and say my temperature must be PV over NK. That if the temperature outside is going to be whatever I get, then this would be a logical answer. So the pressure was 172,375 pascals. That's the temperature the ball is actually were. They still had a volume of 0.004237 meters cubed. But I say they still have the same amount of air in it because we're claiming they were filled to 27 psi at room temperature. And I can solve for this temperature. When I solve for this temperature, I get 271.3 Kelvin. Now I do ask what temperature in Celsius. So I'm just going to take that and subtract 273, and I'll guess that the temperature in Celsius is negative 1.7 degrees Celsius. And so if it was negative 1.7 degrees Celsius outside, this would be a valid excuse and realistic. Negative 1.7 degrees Celsius. Let me do the math real fast. Is just shy of 29 degrees Fahrenheit. That day, it was 40 degrees Fahrenheit. This excuse was made. It was a legit defense, was a legit excuse that the NFL commission and said, yeah, no, your math doesn't work out. And then fined, I think Tom Brady himself got fined something like $4 million or something stupid like that.
That's like a week's worth of pay for him.
I know. But there you go. This was an actual argument that people were actually making and doing the math for at the time. And I had a bunch of diehard Patriots fans in my class the semester this happened, and they like asked about it for the ideal gas law. Like, does it vindicate him? And I was like, nope. And then decided to actually put it on the exam instead because I'm an asshole like that. Any questions here? Let's do another gas one. See, that gas one had only the ideal gas law. I sometimes work in other gas equations. And this one is going to be like that. So this one says, the 2019 Macy's Thanksgiving Day Parade introduced a new SpongeBob balloon that looks like that. It has a volume of 482 meters cubed. And at a temperature of 4 degrees Celsius, it was really cold out. Which 4 degrees Celsius, I don't want to work in Celsius. I'm going to convert to Kelvin. So at a temperature of 277 degrees Kelvin, at a pressure of 152,000 pascals, how many molecules of helium are inside of it? Well, this is the same idea as last time. I'll say PV equals NKT, and I'll solve for n. I'll just divide both sides by kT. And say it would be the pressure times the volume over K times T. If you ever don't get a huge value for n, you know you messed up somewhere. N will always be massive. So part B says what is the total internal energy of the helium? Total internal energy uses the symbol U. And total internal energy is the energy of is how many molecules you have times the energy of one molecule, which is 3/2 kT. It's kind of a weird way to write it like I just did, but I just want to get across it's how many molecules times the energy of one molecule. It's normally written like this, which is how it's on the screen. And so I said, the energy inside will be 3/2 n times Boltzmann's constant times T. That's the energy. Part C. Part C is how fast, on average, are each of these helium atoms moving at? Here's the mass of helium. I actually gave exactly the equation for velocity of a molecule in class. I didn't put it up on the screen. So you could jump straight to that equation. I don't have that equation memorized, so I'm going to really quickly derive it. You see, the kinetic energy of a molecule is 3/2 kT. But kinetic energy of anything, something moving, we know kinetic energy back from chapter 5 is 1/2 mv squared. What I can do is I can multiply both sides by 2, divide both sides by m, and then square root. And as I said, I gave this equation in class. I'm just deriving it again. And so the average velocity of a molecule will be 3 times k times t over the mass, 6.65. Okay, the square root of. And there you go. Any questions? Okay. We'll have to see how this video works when I compile it, since it didn't stop recording apparently. You might get, those of you watching the video might get a little bit of me going like, fuck, and trying to figure out how to get it back online. Not a cursing today. That's what happens when the internet messes up. I curse more. But yeah, there we go. Penultimate chapter. That's everything I got to show you. Next week, we'll do the last chapter, and I have that extra review session on Tuesday of next week. I know I'm going to cover more material on Wednesday, but we'll have covered everything that's going to be on the final by the end of class Monday. The stuff we're going to do in class Wednesday is important. It's worth knowing. You need it for the homework, but it won't be on the final. I'll just spoil that now. So yeah, we'll stop there. Have a good weekend. See you later.